Now for our second example, we have to get the limit of 3n squared minus 1 all over 10n plus 5n squared. Now in this case, n will start at 2 to positive infinity. Now in this case, we have to use the previous theorem on limits as x approaches to positive infinity. If r is a positive rational number and c is any real number, then the limit of c over x raised to r as x approaches to infinity, to positive infinity, is equal to 0. Now, to get the limit of 3n squared minus 1 over 10n plus 5n squared as n approaches to positive infinity, we have to multiply 1 over n squared to the numerator and in the denominator. In this way, we will be able to use the previous theorem. Now, when we multiply 1 over n squared to 3n squared, our answer is 3, since n squared will be cancelled out. And when we multiply the 1 over n squared to negative 1, our answer is negative 1 over n squared. And when we multiply 1 over n squared to 10n, our answer is 10n. And when we multiply 1 over n squared to 5n squared, again, cancel out, the remaining answer is positive 5. Now, with the previous theorem, 1 over n squared is considered as 0, 10 over n is equal to 0, and so the remaining answer is 3 over 5. Now the limit, this is limit 3 over 5 as n approaches to positive infinity. Now remember, the limit of a constant as n approaches to positive infinity is still the constant, which is 3 over 5. And so, the sequence converges to 3 over 5. Hence, this is an example of a convergent sequence. Now, here are some properties of the limit of sequences. Now, if a sub n and b sub n are both convergent sequences, meaning the convergent sequences, meaning the sequences have limits and their limits are not infinity. So number 1, the limit of the sum or the difference of the two convergent sequences as n approaches to positive infinity, this is equal to when we get the limit of a sub n and add or subtract it to the limit of b sub n as n approaches to positive infinity. Number 2, the limit of the product of a constant and a convergent sequence, a sub n, as n approaches to infinity, this is equal to when we multiply the limit, so meaning we will get first the limit of a sub n as n approaches to positive infinity, and then multiply it to c. For number 3, to get the limit of the product of a sub n and b sub n as n approaches to positive infinity, this is just the same as if we are going to get first the limit of each of the convergent sequences and then afterwards multiply their two limits. Number 4, division. To get the quotient of the two convergent sequences as n approaches to positive infinity, this is just the same as when we get first the limit of a sub n and get the limit of b sub n, provided the limit of b sub n is not equal to 0. Afterwards, if we already have the limits of the two convergent sequences and then divide it, so this is just the same as to this. And then to get the limit of a sequence, of a convergent sequence raised to a particular power as n approaches to positive infinity, this is just the same as we get first the limit of a sub n and then raise it to the n power. First few terms of each of the following sequences. So the first one is 4n over n squared minus 7. So here are some of the first few terms. Okay, since there is no indication here and here, so we assume that n will start at 1. That is why we have here n equal to 1. So if n is equal to 1, we just simply substitute 1 here. So we have 4 times 1 over 1 squared minus 7. And so if n is equals to 1, we have negative 2/3 as our a sub 1. So this is our a sub 1. If n is equals to 2, our a sub 2 is negative 8 over 3. If our n is 3, our a sub 3 is 6. If n is 4, our a sub 4 is 16 over 9. Hence, this is our sequence. So we have 0, negative 2/3. These are our sequence terms. Okay? 0, 2, negative 2/3, negative 8 over 3, 6, 16 over 9, and so on and so forth. Another example. Okay, in this case, our n will start at 2. Okay? And so here are our first 5 terms. So if n is 2, so our first term is negative 1 over 13. Okay? So this is, now others will have it as a sub 1 because this is our first term. Okay? This is our first term because we started at 2. But others would prefer it to have as a sub 2. Okay? So that it will not be confused with here. Okay? However, since this is our first term, so others preferred it to have as a sub 1, just to indicate that this is our first term. Okay? So, and this one is our second term, third, fourth, and our fifth term. Determine if the given sequence converges or diverges. Remember, our sequence converges if it has limits, provided that limit is not infinity, and the sequence diverges if the limit is infinite or does not exist. So for number 1, we have 2 raised to n. Now this sequence diverges because as n approaches to positive infinity, the terms get farther and farther apart. So let's see. 2 raised to 1. We assume that n starts at 1 because there's no indication here. Okay. So 2 raised to 1, that's 2. 2 raised to 2, that is 4. 2 raised to 3, that is 8. 2 raised to 4 is equals to 16. 2 raised to 5 is equals to 32. Okay. So as our n, okay, as our n increases, our 2 raised to n, or our a sub n, this is our a sub n. Remember, our 2n is our a sub n. Okay? So as the n increases, our a sub n also increases as n approaches to positive infinity. Our a sub n is also approaching to positive infinity. Okay? 2, 4, 8, 16, 32. So as our n increases or approaching to, so as our n approaches to positive infinity, our answer here is also approaching to positive infinity. Therefore, our limit of 2 raised to n as n approaches to positive infinity is positive infinity. Okay, number 2 example, n squared over n plus 1. So this is our sequence, the general formula for our sequence term. So here is our solution. So the limit of n squared over n plus 1 as n approaches to positive infinity, so we will multiply 1, we multiply it here, so n squared, this is n squared over n plus 1. So we multiplied 1 over n squared in the numerator as well as in the denominator. Okay, we multiply 1 over n squared. Okay, that is why we have this as the answer. So we have n squared over n squared, then here in the denominator we have n over n squared plus 1 over n squared. Okay, and so this one, that is equal to 1. And for this one, we have 1 over n. Okay, 1 over n. And this one will remain 1 over n squared. Again, this is 1 over n because we cancel out 1 n. Now, in this case, our answer is, using the previous theorem, 1 over n is equal to 0, and 1 over n squared is also equal to 0. That is why our denominator is 0. Okay? Now, using another previous theorem, stating that if the limit of g of x, is constant, and the limit of f of x is equal to 0, if c is greater than 0, and if f of x approaches to 0 through positive values of f of x, then the limit of g of x all over f of x is infinite, positive infinity. So that is why our answer here is positive infinity. So that ends our topic on the introduction of sequence as well as the limits of sequences. Thank you and hope you were able to learn something.